potential and how they actually communicate. So action potentials follow what is called the all or none principle. Action potentials have a minimum depolarizing threshold. We spoke about that value, -55. And so at -55, the action potential will happen all the way, right? There is no gradation to the action potential. It's either going to happen or it's not. There is no small, medium, or halfway of an action potential. There is either a full action potential or there is no action potential. And that's what we mean by all or none. Action potentials are also self-regenerative. So self-regenerative means that after one is complete, the conditions to create another one are immediately withheld. So we can have one action potential followed by another one immediately, outside of the refractory period, of course. And so that's what we mean by self-regenerative. So you can always continue to have more action potentials beyond a single action potential. They're self-limiting. So self-limiting means that an action potential will happen and then be complete, okay? So they happen, they last about 1 millisecond, and then they are fully finished at the end of that, okay? They don't linger on, there's no gradation, there's no almost done, there's no difference in time. And so they're very unique, they're identical to one another, okay? They are unidirectional. We'll talk about how that happens along the axon of the neuron. So they only travel in one direction, and that is because of the refractory period. So after we have an action potential along one area of the neuron, that area becomes in its refractory period, and so we cannot fire another action potential there. We can fire one in the adjacent area of the neuron. So that keeps the action potential moving in one direction. Okay. So we can describe different types of stimuli. There are subthreshold depolarizations, meaning we don't have an action potential, and there are suprathreshold depolarization, meaning that we have an action potential. So irregardless of the size of the depolarization or the depolarizing stimulus, the action potential will always look the same, okay? All or nothing. Okay. So I think this pretty much sums up everything I just said. So the size of the stimulus does not matter. We have an action potential or we don't, and it's always at the same amplitude, always at the same magnitude, always of the same duration. Okay, there is no small or big or medium action potential. There is only one identical action potential. Okay. All right, and again, this graph is depicting that same concept. So we have a graded potential here, another one here. We have a threshold stimulus, which gets us to -55. This fires an action potential up to +30. It lasts 1 millisecond. And then we have an even larger stimulus here. But what do we see here? The exact same action potential. Okay, so this is just kind of reiterating that same concept that all action potentials are exactly identical. Okay, so let's walk through this kind of general breakdown of these events. Okay, this is a good time to see if you have any questions as we kind of tie everything together. So we have depolarization of the membrane. This opens up sodium channels, meaning that channels are now open, right? So both the activation and the inactivation gates are open. This increases the membrane permeability for sodium, so sodium begins to move into the cell. This creates that depolarizing event. So we have more positive charge coming into the cell. That creates this positive feedback loop. We're getting further away from our set point of -70 here. And we also want to mention that delayed 1 millisecond event. So after that inactivation gate opened at -55, we've got that 1 millisecond delay, which then closes that inactivation gate, and that decreases the membrane permeability for sodium, which is what closes that gate and stops sodium flow. Okay, when we stop sodium flow, we now have less of a positive charge coming into the cell. So the membrane potential here begins to get more negative or starts to reapproach that of rest. That same 1 millisecond delay also triggers a second event that we talked about, which was the opening of that single gate on the potassium channels, which increased the flow of potassium. So the membrane permeability for potassium is now increased, which we know potassium starts to move according to its ECDF, which is out of the cell, and that feeds into the positive change, the decrease or the negative change of the membrane potential, and it gets back to -70, which is rest. And you know that the movement of potassium is an example of negative feedback, because now we're getting back to our set point of -7. Okay, this is a really good study table. Make sure you understand the events of what's happening here, the timed nature of these two components, right? And then the permeability, right? When the permeability increases for sodium, potassium, etc. Another nice study tool here, this table. Try to clear out the boxes here and try to recreate this from your own understanding of these events. Okay, so two really great study tools to help with this. Okay, any questions there? Any questions so far? Okay, so we're going to move on to the third objective in this packet, which is to describe the refractory periods. We kind of talked a little bit about them. We'll talk more in depth. There are actually two different refractory periods. There's the absolute and the relative. And we'll talk about what happens in the cell to bring about these two periods. Now, because the action potential increases in frequency to a certain point, there needs to be a cutoff for when we can no longer have another action potential. Okay? And so that cutoff is basically during the extent of one action potential. So while we are having an action potential, until that membrane potential gets back to rest, this is said to be the absolute refractory period. Does anyone remember the states of the sodium channel that is responsible for this period? What did we say was the state of that sodium channel that was responsible for the absolute refractory period? Yep, so the channel was inactive, meaning that the channel was closed and incapable of being opened, because although the activation gate is opened, the inactivation gate is closed. So we cannot physically fire another action potential because we cannot move sodium. If we cannot move sodium, we cannot depolarize the cell again, okay? And so that is the absolute refractory period. Sodium channels are inactive at that time. Now, the period immediately after the action potential is complete, so beyond that 1 millisecond here, there is the relative refractory period, and this is due to the movement of potassium. So because potassium channels are still opening, potassium is still moving, potassium is a positively charged ion, it's moving out of the cell, it's creating even more of a negative environment, which you can see here. The membrane potential actually gets down to -85. And so we can fire another action potential here, but we need a really strong stimulus to do so, okay? So physically we can, but it's even more challenging than when the membrane potential is at rest. So the absolute refractory period, we cannot, even if we tried. The relative refractory period, we can, but it takes a really strong stimulus. Think about it. It's going to be harder to get to -55 from -85 than it is to get to -55 from -70. Okay, so an even stronger stimulus will be required to fire an action potential in this period than it would when the membrane potential gets back to rest. Okay, and that is the relative refractory period due to the movement of potassium. Okay. So this slide is summarizing that same concept, right? The big picture here is that the absolute refractory period is due to the inactivation channel on sodium. The relative refractory period is due to the movement of potassium, and then the sodium potassium pump corrects all of this, and then we can get back